So here we've got a set of questions regarding the pKa and dominant species as we look through some acids here. But number one, rank the following acids from strongest to weakest. And they give us three just generic acids, HA, HB, and HC, and they give us their pKa's. I got a pKa of 2.5, a pKa of 5.1, and a pKa of 8.0. Well, if you think about this, um, and why this is the answer, we know that as Ka increases, so too does acidity. Now, it makes sense if you think about HA, just that first acid reacting with that water. It's going to establish an equilibrium where there's some H3O formed and there's some anion, the conjugate base, formed. Well, Ka is just the equilibrium measure of how much this proceeds to the right. So the larger the Ka, the more this reaction is proceeding to the right, then the stronger that acid is. Where this confuses students, though, is that pKa runs backwards of that. So, for example, let's say you have a Ka that's equal to 1 times 10 to the negative, let's say, sixth, versus a Ka that's equal to 1 times 10 to the negative fifth. Well, to find the pKa, you're just taking the negative log of this. When you take the negative log of 1 times 10 to the negative sixth, you end up just getting 6. But if you take the negative log of 1 times 10 to the negative fifth, you end up getting 5. Since you're taking the negative log of it, the power here on this negative 5 and this negative 6 is what's pulling down to yield these answers. Since a Ka of 10 to the negative fifth is higher than the Ka of 10 to the negative sixth, then a pKa of 5 is actually more acidic than a pKa of 6. So we can finish the statement here and clear some space by saying as pKa decreases, so acidity also increases. These two are inversely proportional. As Ka goes up, pKa goes down. So really all I need to do here, in order to order these from strongest acid to weak, I need to find the lowest pKa value first. So HA is the strongest acid. The pKa of HB is 5.1, which is the middle here. So HB will be my middle strength acid. And HC has the highest pKa value, so it is the weakest of these acids. Okay, number two, similar. A weak acid, HA, has a pKa of 6.2. In a solution with a pH of 4.0, which species is more abundant? You can kind of think of this one from two different perspectives. There's a simple comparison approach and there's an equation approach. But what I would do here is I would compare the pH here to that acid's pKa to get an idea of what's going on. So ordinarily, this pKa is representing the balance of the HA to the A minus concentration, the weak acid to its conjugate base concentration. But it's telling us that this solution already has a pH of 4.0. Well, since 4.0 is less than pKa for this acid, that says to me this solution is more acidic than it would ordinarily be here with this 6.2 pKa. Since the acid is the pH rather is too low, I have too much acidic component. So that means that the HA is dominant over the A minus. There's more HA in here than there is A minus because the solution is just too acidic. Really, you could also tie this into the Henderson-Hasselbalch equation where pH equals pKa plus the log of the concentration of the base over the concentration of the undissociated acid. And if you start plugging things in here, you have a 4 for the pH and you have a 6.2 for the pKa. And if you remember, an ideal buffer has equal amounts of the weak acid. Oops, I left off my bracket there. An ideal buffer has equal amounts of the weak acid and its conjugate base. Well, if that's the case, then this cancels out to be a 1, the log of 1 is 0, and this just falls off, leaving you with pH equals pKa if it's an ideal buffer. However, I need to think about what would have to go here in order to figure out, well, what exactly is the concentration here? So take this out of the way. And again, this is definitely the harder way to work this problem, but the log of this guy right here, I'm just going to draw an arrow. If I wanted to try to solve for this, I'd have to subtract 6.2 from both sides. So negative 2.2 equals the log of the conjugate base over the weak acid concentrations. Well, in order to solve for this, it's log base 10, so I need to take 10 to both powers, 10 to the power of both sides, rather. So this would become 10 to the negative 2.2 power is going to end up yielding me the ratio of this anion over this undissociated acid. Well, when I plug 10 to the negative 2.2 in, I end up finding that this ratio here is 0.006, which is significantly less than 1. And if I think about what that means in terms of a fraction, to have a fraction that's significantly less than 1, the denominator must be quite a bit larger than the numerator. And in this case, the denominator is the weak acid. So I can mathematically prove that the weak acid is in a higher concentration than the conjugate base is under these conditions, which really just comes back to this idea right here. If the pH is too low, that means the acidic component is in the majority or it's dominating. Number 3 is very similar. We got the ammonium ion NH4 plus with a pKa of 9.25. We have a solution with the pH of 11. Which species predominates? The part that's going to act as the acid or the conjugate base of it? Well, here, again, I'm going to compare pH to pKa. And in this case, pH is greater than the pKa. That means that there's too much base compared to the acid. So the part that's going to be predominant here is the basic component, the NH3. This is not an ideal buffer, but it's still a buffer because it has the base and the acid component. It's just that I happen to have more of this NH3 present than I do the conjugate acid because the pH is too basic. Moving on to part 2 is just talking about some indicators, and these usually are more straightforward than they appear at first. But number 4, an indicator that is red when the pH is 4.5 is yellow when the pH is 6.5, and we're going to estimate the pKa of the indicator. Well, for an indicator to be useful, we need the pKa to be where the color change is occurring here. So the easiest thing to do here is just to pick the midpoint of these two or take the average of them. Well, what's directly in the middle of 4.5 and 5.5? I'm sorry, 4.5 and 6.5 is 5.5. That is a reasonable estimate for the pKa of that indicator. So we could only use this indicator where we have an acid that also is going to have an equivalence point around 5.5. We want the pKa of that indicator to change where that acid is going to change colors as well. And that kind of piggybacks us into question 5. If we're doing a titration that has an equivalence point at 9, which indicator is going to be best? Well, we need our indicator to change colors near the equivalence point. Well, indicator A changes colors between a pH of 3 and 4. That's nowhere near 9, so that's not a useful indicator here for this equivalence point. But indicator B will change color conveniently between 8 and 9, or 8 and 10, rather. So the equivalence point here of 9 is going to occur within this color change range of the indicator. So indicator B is a much, much, much better choice there for the indicator for this acid with an equivalence point, or this titration rather, with an equivalence point near pH of 9. Part 3, we're just trying to identify which one of these could result in a buffer. Looking at A, I see HF, which is indeed a weak acid. And just as a reminder, any buffer should be a weak acid and its conjugate base, or a weak base and its conjugate acid. So we need to make sure this is fulfilling all those requirements. We said HF is a weak acid. So far that's good. Over here, I'm pairing it with NaF. That doesn't look exactly like the conjugate base of HF, but if you think about what this dissociates into, that sodium is going to make it soluble. So that sodium is going to act as a spectator ion, releasing these fluoride ions. And indeed, the fluoride ion, F minus, is the conjugate base of HF, which is a weak acid. So yes, A is going to be able to produce a buffer. For question B, HCl, that's a strong acid. So right off the bat, I know the answer here is no. This one cannot act as a buffer. It has to be a weak substance and its conjugate, because this reaction has to be able to establish an equilibrium for this buffer to occur, and a strong acid will not establish an equilibrium. That strong acid is going to be completely dissociating into H plus and Cl minus, so there's no opportunity for this conjugate base here to be strong enough of a conjugate base to go backwards. So I cannot use any strong acids or strong bases in my buffers. For question C, I see NH3. That's a nitrogenous base, and it's not one of our strong bases, so it's weak. So far it's looking good. Um, Here, I have NH4Cl, which you might not necessarily know from this, but it's going to dissociate into NH4 plus ions, ammonium ions, and chloride ions. Well, that is then the conjugate that I'm after. Here is my weak base, and here is its conjugate acid once it's accepted a hydrogen ion. So yes, C is also a buffer. D has a lot wrong with it. These are both strong bases. So right off the bat, it's a base and a base, so it can't be a buffer, and they're both strong. So very, very incorrect there on D. And E doesn't even have a partner. So it's not going to be a buffer. I could use the conjugate of this, which would be NO2 minus. If I had some salt that would produce some NO2 1 minus ions, then that would work. But as it stands right now, I just have the HNO2, so it cannot by itself be a buffer. Part 4 is taking this buffer and actually trying to think about the reactions that would occur if an acid or a base were reacted to it. So the easiest thing to do here is let's identify the pieces here. We have HCOOH and HCOO minus. If you remember in class, we talked about this carboxyl group right here, this COO group, and we know that anytime you see this carboxyl group, it's going to act as a weak acid. Further indications here that that was a weak acid is look at the difference. You lost an H moving to this HCOO1 minus ion. So that means since this guy right here lost an H, he must be acting as the acid. Then this must be the conjugate base, which makes sense because now he could reaccept an H and act as a base and go backwards. So let me clear this up a little bit. We've established that this is my weak acid. This is the conjugate base of my weak acid. So then for part A, I'm adding an acid. Well, it makes sense which part of this buffer is going to react with the acid. It must be the basic component here. The basic component is HCOO minus. It's going to react with that HCl. Any acid and base reaction is going to go to completion, so it's not got an equilibrium arrow. It just has a one-directional arrow. And since this is a base and this is an acid, the H must be donated to the base. So that's going to leave me here with the Cl minus. And then my conjugate base is accepting that H, so it's going to take me back to my weak acid, COOH. And there's my reaction. Notice all of the acid was neutralized, so this pH won't change very much. For part B, I have the addition of a strong base, so that means I need the acidic component to react with it. HCOOH plus that base NaOH. And again, we know this is a base. He's going to accept an H, meaning it has to come from this acid here. So the easiest thing to do first is take the H from this HCOOH, which means I'll have HCOO minus. Plus, gotta be a little bit careful not to get lost in the weeds here. This hydrogen was donated. It's going to react with the OH here, which will just form water. Then the question is, well, what happened to the sodium? Well, the sodium was just a carrier of the OH anyway. He's just a spectator ion, so he's still just going to be floating around over there. It is possible that you could write this equation and cancel out the sodiums here and here, but you could also argue that it's possible then to cancel out the chlorines up here. So it doesn't really matter whether you cancel those out or not, but I just don't want you thinking those spectator ions do anything here other than carry the other component into the reaction. Number 5 is actually some calculations with the Henderson-Hasselbalch equation. So we'll start with number 8 here. Calculate the pH of a buffer. So right off the bat, pH of a buffer is the Henderson-Hasselbalch equation. pH equals pKa plus the log of the A minus concentration, the conjugate base concentration, over the weak acids concentration. So we're finding the pH. I know I'm looking here for pH for my final answer of a buffer that contains 0.2 molar HC2H3O2 and zero point 0.4 molar of C2H3O2 1 minus. Now be really careful, and let's go ahead and identify these. This is my weak acid. I can see it donated an H that this guy has no longer got, so this must be my conjugate base. So this weak acid concentration is what's going to go right here in the Henderson-Hasselbalch equation. And this conjugate base concentration is going to be what goes right here as my anion concentration. The only thing that we don't really have here is the pKa, but I was provided the Ka, 1.8, let's not miss that, times 10 to the negative fifth. So to find the pKa, I just need to take the negative log of, I did not give myself enough room, 1.8 times 10 to the negative fifth power. We just plug that into a calculator real fast. Negative log of 1.8 times 10 to the negative fifth gives me a pKa of 4.745. And that's going to be my pKa for which I'll plug in right there. Okay, so it's just a matter of plugging this in. However, I do want to point out this has a larger basic component than it does an acidic component. That means this is going to be more basic than what I would have expected if they were equivalent. And if they were equivalent, remember all this cancels out. So that would have just left me with the pH equaling the pKa, and the pH should have been 4.745. Since this has a larger basic component than it does acidic component, I'm going to expect this answer to be more basic than a perfect ideal buffer. So just keeping that in mind, this answer had better be larger than 4.745. So let's go through and plug in. pH equals the pKa for this weak acid, which is 4.745, plus the log of the conjugate base component of 0.4 over the weak acid component of 0.2. And you can just plug this into your calculator. This is going to end up yielding us a pH of about a 5.04, which does make sense. This pH is more basic than the Ka, which means I have a larger component of conjugate base than I do weak acid. Number 9 is looking pretty similar. A buffer has equal concentrations of NH3, which is a weak base, and NH4 plus, which is its conjugate acid. The pKa of the conjugate acid is 9.25. What's the pH? Well, if it has equal concentrations, then pH has to equal pKa. And again, this log part is going to fall off if these concentrations are equal. And the reason for that, just in case math's not your favorite subject, you're taking the log of the conjugate of that acid over the acid. And if these two items right here are the same, then you're ending up taking the log of 1, and the log of 1 is 0. So all this is going to fall off and be irrelevant. This just means the pH equals the pKa. This is an ideal buffer, so that means the pH is also 9.25. Number 10 is probably one of the most out there questions, but a question was actually asked on the 2025 AP exam just like this. We've got a buffer that has a pH of 5.4, but its pKa was 4.4. Well, that's telling me had these had equal amounts of conjugate base and weak acid, then the pKa should have equaled the pH, and it doesn't. Instead, the pH is too basic. Too basic. So I'm going to have more of the conjugate base than I do of the weak acid. So when I solve for this ratio here, I should end up with something that's more than 1 because the numerator is going to be larger. But this is still just a Henderson-Hasselbalch equation. We just don't have to solve it in its conventional way. pH equals pKa. Oops, not equals, sorry. Plus the log of the A minus concentration over the HA concentration. And just look at what you know. You know the pH is 5.4. The pKa is 4.4. Plus the log of all of this. Forgive me for not rewriting it. I need to solve for that log, what's inside that log. So I'm going to just subtract 4.4 for both sides. This gets me a 1.00 difference is equal to the log of the conjugate base over the weak acid. Oops, not like that. Let's do a bracket better there. Okay. Well, this is log base 10. All of our pH scale, all these things are log base 10. So to cancel out a log base 10, I just need to take 10 to the power of both sides. So 10 to the first power, which is equal to 10, is going to equal 10 to the power of this entire log. And what you're going to find is the log and the 10 cancel out, which leaves me a fraction of the conjugate base divided by the weak acid. Well, if this guy's fraction right here equals 10, then that means it's a 10 conjugate bases for every one weak acid. So my ratio here is 10 to 1. The conjugate base is 10 times as concentrated as the weak acid, which actually leads to an interesting discussion here. This is 1 unit of pH more basic than it should be, and every movement of 1 on the pH scale is a times 10 change in acidity. So it makes sense that to have an even change of 1, the base must be 10 times as concentrated as it ordinarily would have been. Part 6 is talking about titrations, and number 11 specifically is the titration of a weak acid with a strong base. This isn't what the question's asking, but it is worth noting that at the equivalence point, then, this is going to have a pH greater than 7 because it's a weak acid with a strong base. But what's true at the half equivalence point? Well, as you add strong base and weak acid, some of this weak acid, let's just call it HA, gets turned into, as it gets reacted with that base, gets turned into its conjugate base. Well, at the half equivalence point, half of this HA has been removed, which means that the 50% that was gone is now A minus. Half of the HA has been turned into A minus, which means the concentration of the HA has to be equal to the concentration of the A minus at that half equivalence point. That's important back to the Henderson-Hasselbalch equation. If you're halfway to the equivalence point, then you have equal concentrations of these two, which means it's an ideal buffer, which means the pH has to equal the pKa at that half equivalence point. And number 12 is exactly the same, just worded a little differently. You've got a titration curve that shows the pH at a half equivalence point is 5.8. What's the pKa? Now, I guess it really probably should have specified that this was a weak acid, strong base, or a strong acid, weak base, but we're going to assume it is. Um, at the half equivalence point, half of that weak substance has been turned into its conjugate base. So the two concentrations equal. Again, the pH just has to equal the pKa then. So the pKa of this acid is a 5.80 because that was the pH at that half equivalence point. And part 7 is buffer capacity number 13, which buffer is going to have the greater capacity. And the idea of buffer capacity is just how much acid or base can this buffer absorb before the buffer gets destroyed? And it's destroyed when you run out of either weak acid, conjugate base, or one of the other. When you run out, the buffer's over. So it just makes sense that the greater the number of moles of weak acid and conjugate base, the higher the buffer capacity. That means buffer B is going to be the better buffer. It has a 10 times the concentration of conjugate acid or weak base and conjugate acid. So it's going to be able to buff 10 times as much acid or base being added to it. Because think why. If I added zero point 0.2 moles of, let's just say, some strong base, OH, that's going to wipe out every bit of this HF, assuming, I don't know the volume here, but assuming I don't have, let's say it's 1 liter to make the math easier. I don't have zero point 0.2 moles of acid to react with this, so this buffer is going to be destroyed. I will run out of acid and the buffer will no longer have any buffering capacity. But if this right here is occurring in a 1 liter solution, then I have 1 mole of HF. That's plenty of HF to react with this 0.2 mole of OH. So buffer B is going to have the higher buffering capacity.